So this video is a quick overview and demo of our paper towards a universal image degradation model via Content-Degradation Disentanglement. This paper is to be presented at ICCV 2025. Image degradation modeling and synthesis have a wide range of applications in the field of computer vision and image processing. It is useful in image restoration, data augmentation, and simulating artistic effects such as film grain. However, existing methods are rather limited. Each model is labor-consuming for researchers because currently researchers need to design a specific model for each downstream application, and the design of such models requires strong domain knowledge in the specific application. Existing methods also have difficulties modeling localized degradation. Furthermore, existing methods often require supervision on degradation parameters, which are usually unavailable in real-world scenarios. Our contributions can be summarized in three aspects. First, we propose the first universal degradation model. Our model does not have downstream application-specific design, so it can handle all types of degradations, including both global and localized degradation. Second, we propose a novel disentangle-by-compression method, which enables our model to learn disentangled degradation representation without explicit supervision on degradation parameters. This allows us to manipulate individual degradation components after learning. Third, our model can be plugged into downstream applications without significant modifications. In particular, our model can convert existing non-blind inversion-based image restoration methods to blind methods. Our model is trained to extract degradation information from one distorted image and reapply it to the clean version of the image. The result is a perceptually indistinguishable image from the original distorted image. Our model is trained to extract degradation information from one distorted image and reapply it to the clean version of the image. The result is a perceptually indistinguishable image from the original distorted image. Thanks to the degradation disentangling techniques we developed, our model can extract degradation information from one image and apply it to another unrelated image. It is worth noting that the model learns to transfer degradation without being explicitly supervised on such task. These are the test results on the Wikimedia quality image dataset. In this figure, degradations, reproduction, and transfer are shown. Each diagonal entry indicates the reproduction performance here. We extract degradation from an image and apply it to its clean version. All other entries indicate the transfer performance here. We extract degradation from an image and apply it to an unrelated image. The results on the WQI dataset benchmarks our model's generalizability to image content. So these are the test results on the raindrop dataset. The results demonstrate our model's artistic applications in simulating weather effects. These are the test results on the BERT dataset. The first line shows images in the E dataset with real-world motion blur. The second line shows the clean counterparts of the images. The third line shows the images with motion blur synthesized by our model. The results demonstrate our model's artistic applications in simulating realistic motion. These are the test results on the film grain style dataset. The results demonstrate our model's artistic applications in simulating film grain effects for the movie industry. Our model has significant advantages over existing degradation models. Most existing models are degradation specific and cannot be adapted beyond just their original purpose. Chen et al.'s model is the only model with degradation agnostic architecture, but it requires a separate training for each degradation type. Our model can handle multiple degradation types with a single training. Another related field to compare is style transfer. However, even the state-of-the-art style transfer model such as Dieter has difficulties learning image degradations. The model fails at separating distortion from content, hence alters skin tone and texture while not transferring distortion. Our model solves these problems. Our model can identify independent degradation components. There are 5 independent degradation components like our model identified from the WQI dataset. Our model can be plugged into inversion-based image restoration pipelines. It works with any underlying generative model for any image contents. We use robust style-gain inversion as an example. It excels at restoring images with the degradation process in the ground truth degradation parameters are not. If the degradation information is not available, it cannot redistort the image in the restoration pipeline, causing severe artifacts in the result. Plugging in our model allows RC to restore images without requiring degradation information, significantly improving its practicality. More visual examples are available in the technical supplement. Our model can also be plugged into diffusion posterior sampling for diffusion model inversion-based image restoration. Please feel free to check out our project page and other projects from our lab.